Our inaugural speaker, Rebecca Leane, sorry, I knew I would stumble over this, from SLAC at Stanford. Rebecca did her PhD in Melbourne at 2017, and then moved to MIT and Stanford for postdocs, where she made a splash by playing a major role and continuing to play a major role, figuring out the origin of the galactic center gamma ray excess and its possible connection to dark matter. This is ongoing. And she became a permanent staff scientist at SLAC in 2021. She's one of the world leaders in understanding dark matter and its detailed astrophysical interactions, including in cosmic rays and in its capture in planetary or stellar environments, some of which we'll hear about today. So we're very lucky to have her here. So please join me in giving her a warm welcome. Thank you.
Okay, thanks very much, David, for the nice introduction. Thanks everyone for coming along today. It's really a pleasure to be here in person and have lots of interesting chats with all of you. So today I'm going to tell you about dark matter and how we can potentially detect dark matter in stars and in planets. So to start with, what do we know about dark matter? What is it? We think that it makes up most of the matter of the universe. So about 85% of the matter we think is dark matter, rather than the regular matter that we're all made up of. And we think that it doesn't interact very much with light, which is part of why we call it dark matter. And these two pieces of information about dark matter we get from something called the cosmic microwave background. And that's pictured here, which is this early relic radiation from the early universe. We also think that dark matter provides the large-scale structure, and in fact, a lot of the structure we see in our universe. And this evidence comes from things like n-body simulations, and that's what you can see in this really nice simulation here. On large scales, we see kind of like a web-like structure of all of the visible matter. And if you don't have dark matter, you just don't get this structure. So dark matter seems to give us the backbone of a lot of the structure in our universe. And because of this, we also think dark matter is, at least most of it, is not relativistic, because if it just moves too fast, it can wipe out structure that we do actually observe. We also think that dark matter forms halos around galaxies. And this actually was one of the earliest pieces of evidence we had from dark matter, which is just when we looked at galaxies out in the universe, the speed in which they're rotating seems way too high for how much luminous matter they actually have, which seem to imply we need some additional component, which we think is dark matter. So there's much more mass in a galaxy in dark matter than regular matter. So these are a few of the things we think we know about dark matter. And really, the evidence for dark matter is really overwhelming. So we see it across many length scales. We see it in many, many different systems. It seems to be there, and we don't really know what it is. This dark matter cannot be explained by any known particles. So the particles we're made up of, we don't think this is dark matter. It has to be something new, something not in our standard model of particle physics. So those are the things we think we know about dark matter. But in reality, the amount we know is really tiny. So there's so much more we don't know about dark matter than we actually know about it. So first of all, what is it made of? We have no idea. We don't know if it's one particle, if it's many particles, and how these particles might interact with each other. We don't know where dark matter came from. So we don't know how it was produced in the early universe. And if it was made somehow in the early universe, we don't know how it might have changed over time to what we observe today. And importantly, we don't know if it interacts with the regular matter, which is us. All the evidence to date we have for dark matter comes from its gravitational interactions in astrophysics and cosmology. And it's possible it doesn't interact with us at all. Hopefully it does interact with us because we would like to detect it. But also there are some good reasons to think maybe it does interact with us, and maybe some rich sector of the dark sector is detectable by us. So if we sit in this sort of picture of knowing almost nothing about dark matter, how do we find it? If you're a particle theorist, this is an extremely difficult problem. We have no idea what it is, how it interacts with us, what mass it has, almost nothing. So what do we do? This is a tricky sort of position to be in. There are lots of things we try to do, lots of different approaches. But in my talk today, I want to focus on one that's the most exciting to me, which is my research program, which is understanding dark matter through astrophysics and cosmology. And the reason why I think it's really exciting to use astrophysics to try and find dark matter is simply that it's dark matter's natural habitat. All the evidence for dark matter comes from astrophysics and cosmology. We see it modifying the dynamics of galaxies, all these different large structures. So it seems like the natural place to go and understand it some more, at least understand if it's a particle and how it might interact. And I also like using astrophysics because really you can have a lot of fun. There are so many diverse systems with diverse properties that really give you a playground of ideas you can use to think about new signatures of how dark matter might appear. So I like to think about new searches in a really broad sense. Because remember, I just said we know so little about what dark matter is. It's good to try and stay really agnostic as to what its fundamental nature is and cover as broadly as possible, as many opportunities as possible, just thinking about what general signatures might cover as many particle physics realizations as possible. The other reason why astrophysics is interesting is right now and in the coming decade, we are going to have so much new data. I'm going to tell you about some of the new telescopes that we'll have in the next decade or so and what they can tell us about dark matter. And I think really now is the time to start thinking about how do we exploit this diverse range of systems with such an enormous amount of data across so many wavelengths. So as an outline of the search ideas for dark matter I'll tell you about today, I'm going to be focusing on how dark matter can become captured by stars and planets and a range of observable signatures that we can use to try and hopefully uncover its fundamental nature. So I'm going to explain how dark matter can actually become captured in these different stars and planets that I'm calling celestial objects. I'll talk about the ideal properties of different celestial objects. So there is so many different systems you can use, and it turns out they're actually optimal in different regimes. So depending on the fundamental nature of dark matter, different stars or planets will be the most optimal type of detector, it turns out. And I'll tell you about the search locations in our universe that we'll want to use to try and find dark matter using these objects. So I'm going to cover two types of searches, well, really maybe three types of searches in this talk. There are so many more. So I'll try and give you a hint towards the end of even the broader range that we have, but I can only focus on a few today. One will be heating searches, so where dark matter actually heats up stars and planets. And this will cover a range of objects, including our own Earth, white dwarfs, neutron stars, and even exoplanets. I'll tell you towards the end about new neutrino and gamma ray searches we can do using the sun, Jupiter, and full populations of stars and planets. All right, so the general idea of how dark matter actually becomes captured by a star or a planet is that in our own galaxy, as I said earlier, we have a lot more dark matter than we do compared to the regular matter. And throughout this galaxy, we have lots of stars and planets peppered throughout the dark matter halo. So what can happen is, under the assumption that the dark matter does interact with the standard model, so interacts with us, the dark matter particle can scatter with the surface of the star or the planet. And when it scatters, it can then lose energy. So if it loses sufficient energy upon scattering with the star or the planet, it can become gravitationally captured. So if it loses enough energy, what actually happens is over time, more and more of these dark matter particles will keep falling into stars and planets, and you'll actually build up a very large population of dark matter particles inside all the stars and the planets in our galaxy and in other galaxies. So the question then is, what happens if you have so much dark matter building up inside these objects? Dark matter will change their properties and give you a bunch of really exciting signatures. So just to give you one example now, something that can happen is if you have a lot of dark matter particles and they're building up, if dark matter is the type of particle that annihilates, so if we have like matter and antimatter for regular matter, we know that can just annihilate. Dark matter can do the same sort of thing. So dark matter particles, antiparticles, just like our regular visible sector, particles will just smash together and annihilate and release energy. So the dark matter particles will release their annihilation energy inside the star or the planet. And consequently, if it releases this energy, it just increases the temperature. So if dark matter is being captured by all these objects should have much higher temperatures than we would expect if dark matter didn't exist and didn't interact in this way. So this is one example. I'm going to go through a few different objects and the prospects for finding dark matter using this. Before I do so, I want to tell you about what is the optimal star or planet to use to find dark matter? And this is actually a fun problem. And it turns out there isn't just one star or type of star or one type of planet that actually is the best. Different stars, different planets are actually better in different regimes. And what I mean by that is depending on the fundamental nature of dark matter, one object might be better compared to another one. Depending on what environment you're actually doing your search, you might find one is more optimal than another. So what sort of properties are good when we want to look for a good star or planet to find dark matter? One of the most obvious things is just if it's big. So if it has a big radius, this really just means it has lots of area, so it has lots of space to try and capture dark matter particles. So the chance that dark matter as it's flying by actually intersects is much higher because it just has a large space to intersect with. So generally, big stars or planets are pretty good. Smaller ones, usually not as good. The other thing that's good, a good property to have is high density. So if a star or planet is very dense, generally what this means is just that you have very good sensitivity to weaker interactions. And the reason for this is just that even if dark matter doesn't interact very much, you can have a very strong gravitational field that can pull you in. And you also can have lots of particles available for the dark matter to actually scatter with and become captured. A third feature is a low core temperature. So if an object is very hot, this usually isn't so good for thinking about something like heating. And that's for two reasons. One, of course, if it's so hot that you can't see the dark matter heating, then okay, you don't even want to use that object. But there's another process which is called evaporation. So if a dark matter particle comes in, for example, our sun, and it interacts on the inside, it inherits some temperature from the solar environment as well. And what can happen is if the interior is too hot, it gives a very solid thermal kick to the dark matter particle. And this thermal kick can be so big that it just overcomes the escape velocity and then just leaves. So if the dark matter particle is just getting ejected because the object's so hot, it just keeps giving all these thermal kicks, you'll never actually be able to probe any of these signatures because dark matter tries to go in and it just gets kicked right back out. So generally, colder objects are really good at retaining even lighter dark matter particles. So with those features in mind, is that all that matters when we're picking what target to use? Another thing, I guess, is kind of obvious, but it's important to state, is that the signal detectability matters. So you might say, I don't know, some particular object sounds like it's great, we should use that. But of course, if we put it on the other side of the galaxy and you can't detect it with your telescope, it's useless. So we have to think about what place in the galaxy we want to go looking for dark matter using one of these objects. So, if you're much further away, you have a 1 on r squared suppression, so 1 on the distance squared. So the flux is going to decrease. So you have to have a telescope that really has sensitivity high enough for potentially much lower flux if you want to look at something very far away. And then if you're considering what object to use and you do want to go far away, you want to use something very big so you can still see it with your telescope. So the luminosity of any of these objects goes like a surface area. So when they're tiny, you can only really do a search in the local position. You don't want to go too far away. Okay, so those things in mind, here is the scope of what people generally think about as different locations to find dark matter using a star or a planet. And there are lots of different locations that are better suited to different stars or different planets. So one of the most classic places to go looking is just the local position. So right where we're sitting here. And the reason why the local position is good is you can imagine, of course, the flux can be, that we can actually detect is very detectable, can be quite high, just because it's close by. So close by is good. The drawback is actually the amount of dark matter that we think is in the local position is much lower than other places in the galaxy. So for some objects, if we want to make sure we have a very large dark matter annihilation rate, so a very large heating rate, we might want to look in a place where there's more dark matter available. This will depend on the object. So local position is great because the flux is large, but not so much dark matter in that sense. Another place people look called globular clusters. And so these are just clusters of very old stars. And the reason why they can be one of the best places to look is simply because according to some research papers, there might be a lot of dark matter in them. So this is actually a little bit controversial. Depending on what paper you look, which paper you look at, you'll find actually there's a different answer for how much dark matter should be in those. So that's why this has a bit of an asterisk. If it's really as large as that, maybe it's actually very, very small, the amount of dark matter. In any case, there is much more dark matter potentially in these objects. So maybe you want to consider that in some cases. And then the other obvious place is the center of our galaxy. So the center of the galaxy, we think from simulations, has a lot of dark matter. It has a lot of dark matter. This is somewhat more certain than something like a globular cluster, and it's definitely higher than the local position. But then you're going to have the problem of, well, it's very far away, so the flux will decrease. So overall, the features that we want for environments or just search locations are high dark matter density, lots of dark matter there that can power a very big signal, a low dark matter velocity, because if it's moving very slowly, it's very easy to actually capture it and have it be drawn in by the gravity of the star or the planet. If it goes too fast, it can just go past. If it's moving very slowly, you can have something called gravitational focusing that more easily pulls the dark matter particles in. And then close by, ideally, some old environments, so backgrounds are fairly low, and then we don't want dust getting in the way, which is always a problem in astrophysics. So if we start trying to look in the center of the galaxy, we have problems with dust, which I'll get to shortly. So of course, you might notice these features all look great, but you're probably not going to have all of them at the same time. You might have a high density, but not be close by. You might have one of these features, not the others. So depending on what star or planet you're using, a different location will be optimal. So before I actually dive into the results that we have so far and what people have done so far to try and understand where dark matter is and what it might be, let me just recap what I've told you now. So I told you there are lots of different celestial objects. They have unique temperatures, unique sizes, lots of different densities. Different objects will be optimal for different interaction sizes or for different dark matter masses. Lots of different search locations, optimal in different regimes. And there's a variety of dark matter signatures in celestial objects that are possible. And I'm going to now consider dark matter heating, this one where we say dark matter annihilates. It just inserts its mass energy into these objects and increases the temperature. And we're going to talk about this for many objects now in many locations. So if you're ready, let's start with dark matter heating. What's we want to use for dark matter heating? First thing you would think of, maybe close by, the sun, not so good. Sun's very hot. We don't want something hot. We want something colder. And something colder, well, we have lots of those. We have Earth that we're on here. So this is cold compared to the sun. We have something like Mars or Jupiter. So just solar system planets are great for dark matter heating. We can also think about other planets around other solar systems, as well as neutron stars and white dwarfs. And I'll tell you about some of these briefly. First, what type of telescopes do we want to actually use to try and detect this signal? Well, this is the range that we're targeting. So the coldest stars or planets are around 50 Kelvin. So these are the ones, usually planets that are very old. At best, usually they're even warmer than that. And if you're around 50 Kelvin, you're kind of the bottom end of the infrared. So if the planets without dark matter are about 50 Kelvin, that's already your baseline. So if you add so little dark matter that you don't increase above 50 Kelvin, you don't see anything, so it's not so helpful. So we want to increase the temperature above 50 Kelvin, which means we want to go from the bottom of the infrared up. So we want to use an infrared telescope or something even higher. It turns out you can actually push up all the way into the UV or even X-rays if you pick a very high density dark matter environment. Problem is, if you start going into UV or X-rays, you can have something called dust extinction, which is just that these very high energy rays don't do a very good job of getting through the dust and actually seeing them. So depending on where we're looking, if an object gets heated into this range, we might not be able to see it. But overall, really, infrared optical is a very good place to look. And what do we have to look in the infrared optical? This is why I think this field is really exciting right now. We have so much new data coming very soon, and we actually have some data we can already use. So one is the absolute classic Hubble Space Telescope. I think everybody has heard of Hubble. It is absolutely amazing. It's focused in mostly the optical. It can actually do a little bit of near infrared as well. And Hubble was launched a long time ago, 1990. And it's still taking data. And it will take data, I think, still for a while just yet. And so if dark matter heats any star or planet into the optical, in principle, Hubble could have seen it. And we have some data from Hubble already that I'll show you briefly in terms of results for this. Another one, which is my favorite maybe at the moment, is JWST. So this was supposed to launch a very long time ago. And finally, on Christmas Day of 2021, it launched. This was, I think, at 4 or 5 a.m. in California where I was. I watched it live. I was that excited. I was very happy to see the launch went all okay, and it's all up and taking data. And I guess many of you have already seen the amazing images coming out of this telescope. It is extremely powerful. It's an absolute powerhouse of what it can do. And it turns out, actually, this telescope is going to be great. It's going to play a key role in trying to find dark matter in stars and planets, which you're about to hear about in the rest of the talk. There are other two telescopes I'm really excited about, both Rubin and Roman. So these can do, well, if you're looking at Rubin, the near infrared and optical, very powerful, hopefully actually starts taking, well, has first light later this year. And Roman is more on the timescale of the next 5 years or so, but this can do near infrared and optical as well. So all of these are going to have an important role in finding dark matter. And so much we're going to learn. So let's start now going through all the different objects. What is the data we have? What have we learned about dark matter from all these different stars and planets so far? And what are the prospects going forward? So first of all, Earth seems the most obvious place to start. It's our own planet. Dark matter could heat up the Earth. So dark matter particles come into the Earth, annihilate, increases temperature. And the reason why, a main benefit for the Earth is really just proximity and systematics. And the amount of data we have on the Earth is really great. So actually, there's something like 20,000 boreholes dug into the Earth's surface. Some of them go, I think the deepest one is something like 12 kilometers down. And geologists have been studying the internal temperature of the Earth, or the heat gradient of the Earth, for a long time. So we have a lot of data already on this. And based on this data, the geologists have thankfully already taken for us, we can have a look at the temperature that's measured and compare it to what we might expect from any background, or whether or not it could be dark matter actually heating up our Earth. So the benefits, systematics are low. We have lots of data we've measured ourselves on our own planet. We have the data now, best proximity. The limitation for the Earth is because it's small compared to other things you could use, like the sun or maybe Jupiter, it doesn't do as good of a job at keeping dark matter trapped. So I told you about this process where dark matter particles they come inside, there's some temperature in the star and the planet, it can give it a thermal kick. Because the gravitational field isn't as strong, and the Earth has something that's maybe more dense or a bit bigger, the particles more easily just kind of leak out in this evaporation process. So it can't go down to as low masses in the dark matter sort of parameter space, but we can still do something. So this was actually pointed out well, people worked on dark matter in the Earth like 30 years, 20 years or something. But there was this really nice paper in 2007 that pointed out you could have unprecedented sensitivity to the dark matter parameter space using the Earth. So the result isn't actually shown just yet. On the y-axis, this is the dark matter interaction rate with nucleons. So in particular, it's the cross-section for scattering. So you can think about, you just have nucleons sitting on the Earth, the dark matter particle comes in, interacts, bounces off. So it's just that the size of that interaction. On the x-axis, this is the dark matter mass. And we have lots of other experiments that exist that do not use stars and planets, more kind of well-studied experiments. So there are many underground detectors. This is called direct detection, if you're familiar with this. And this is from 2007, so some of these results have actually been updated since. But here at the time was the constraint we had using underground experiments. And then there was a bunch of constraints from astrophysics. But once you put on the constraint from the Earth, you actually see, you fill in at the time, lots of different gaps that we didn't have before. So the Earth really actually does have constraining power for the fundamental nature of dark matter, which is fun. But is it the best object to use in all regimes? Not the best object in every case. One that you can also use are called white dwarfs. So white dwarfs are something that's about the size of the Earth, but they're much more dense. So they have roughly a solar mass, depending on what white dwarf you're using. But because of the size of the Earth, this means the density is really high, and they're very efficient at capturing dark matter particles. So the escape velocity is much higher, you see, compared to the Earth's roughly 11 kilometers per second. So particles can get trapped very easily, which means you can have very good sensitivity to fairly weak interactions. And if you haven't heard of a white dwarf before, this is just something you get when a main sequence star collapses. It depends on what the mass of the main sequence star was before its collapse, if you get a white dwarf or something else. And this is just supported against the gravitational collapse by electron to density pressure. All right, so what data do we have for white dwarfs? For white dwarfs, we actually want to use the Hubble data. And the reason we want to use the Hubble data is because white dwarfs are quite big and very efficient at capturing dark matter particles. Because their background temperature also is actually quite high. They're not like the Earth that's kind of sitting there as some rocky planet. They can be quite hot. So if they're already hot and you try looking for one in the local position, you just won't have enough dark matter heating to overcome the background expectation. So while they can capture a lot of dark matter, you need to put them in a very high density dark matter environment to overcome this background. So that's why we want to put them into globular clusters, this environment I told you about earlier in the talk where we think maybe there's a lot of dark matter, and we don't have a problem with going further away, so further from the local position to use a white dwarf, because white dwarfs, if they're about Earth size, are sufficiently big, it turns out. If you want to put something that size that far away with the luminosity we expect, you should be able to detect it. And for white dwarfs, you'll heat into the optical, because as I was saying, they're very efficient, they capture lots of dark matter. So Hubble is perfect, and actually we already have Hubble data looking at white dwarfs in these really potentially dark matter dense globular clusters. So the main limitation with this type of search using these white dwarfs and globular clusters is just that, as I said, we don't know if the dark matter is there. So it has a pretty big caveat. We have to assume it's there to actually get any constraint. It benefits, we actually do have white dwarfs existing in globular cluster cores. We do have the data, and they give us very good sensitivity to a wide range of parameters. So the status using white dwarfs at the moment is what's shown here. So the y-axis is, again, the dark matter interaction rate with the standard model. So this one here is just proton scattering, dark matter scattering of protons, interaction size. And the x-axis is the dark matter mass. The shaded regions here and these deep underground experiments, and the blue line across here is approximately the sensitivity you could get using white dwarfs in these really high density globular clusters. So anything above this line, in principle, will be ruled out if you accept there is actually dark matter in there. But one thing that you can see really is that this is going to much, much lower values in the interaction rate than the Earth could, because these things are just so dense, they're very efficient at capturing dark matter particles. The next object, and this one is really like the boss of the stars and the planets and has been the boss for a very long time. And you might notice that I've been showing on the side a list of some papers where people have thought about dark matter in the object I'm telling you about. This is a non-complete list of dark matter and neutron stars, not even close to complete. In fact, I think most of this list is just this heating signature. There's so many other types of signatures and other things you can do. The reason why neutron stars have been so popular is these are also like the most dense thing you're going to get. So neutron stars are tiny. They're only something like 10 kilometers across in radius, pretty small compared to the Earth or compared to any other sort of like main sequence star. But they have a whole solar mass packed into this tiny, tiny, tiny volume, which just makes them like the monsters. So dense, so efficient at capturing dark matter particles. And in fact, they're actually so efficient that when dark matter tries to fall into a neutron star, it gets sped up to close to the speed of light when it comes in. And because it's coming in at close to the speed of light, there's a massive amount of kinetic energy that just gets deposited inside the neutron star, which can make them heat up actually quite a lot. So neutron stars, if you haven't really been thinking about them before, are really just collapsed cores of very heavy, very, very heavy stars. So usually more like 10 to 25 solar masses, so bigger ones than those that make white dwarfs. And these are supported against gravitational collapse by neutron degeneracy pressure and nuclear forces. So what can we do with neutron stars? I said they're the boss, but are they actually the boss in terms of how well you can detect them? I don't think they are in terms of how well you can actually detect them. They're in principle the best thing to use, but remember I emphasized earlier, what really matters is how detectable your signature actually is. So we don't have data yet from any neutron star that we could actually use for this dark matter heating. And this is because to actually be able to detect the neutron star and the amount of dark matter heating we expect, you need to have a neutron star in roughly the nearest like 100 parsec, which is on the scale of the galaxy, actually extremely close by. And they have to be sufficiently old because when they're young, they can be very hot and you wouldn't see the dark matter heating. So you need something like 10 gigayears in age, which is kind of old. So you need an old neutron star, you need one very close by. You have to find it, and then you have to actually get the data from it. So it's this tiny little thing hanging out by itself, being old, being cold, close by. So we have to find that, and there's no guarantee we even actually would find it. So there's limitations, but the benefit really is you get superior interaction sensitivity. That's the main thing. So this is a sort of a projection for what you could expect for dark matter and neutron stars. The y-axis, again, dark matter interaction rate with the standard model. So this is just bouncing off the neutrons in the neutron stars. And the y-axis, sorry, x-axis, again, is just the dark matter mass. And you see here, this dashed blue line is assuming all the dark matter that passes through the neutron star gets captured. And in terms of how far down this goes in the interaction rate, this is tiny compared to all of the other objects. All the other stars and planets you could use don't go down this far. And the other sort of curved lines here are these underground experiments that already exist in the lab. So for light dark matter masses, potentially neutron stars could be our best bet at finding dark matter. But a few things have to align. So we have to find these small little things hanging out very close by and being fairly old. All right, next one, and actually my favorite of all of them are exoplanets. So exoplanets might sound very bizarre. Why do you want to use an exoplanet when we already have planets, for example, in our own solar system? We have the Earth, we have Jupiter. Why would you ever want to go use a planet in another solar system? There's actually many benefits to using exoplanets, and I think they can actually be the best dark matter detector, at least in some regimes. So one of the benefits really is that the exoplanet research program right now is exploding. So we didn't even know exoplanets existed until something like 1990. And the bulk of the exoplanets we've found has really been in the last decade. Even the last 5 years, it's increased dramatically how many we find. We're finding so many more new planets all the time. And there are many telescopes, some of the ones that I mentioned to you earlier in the talk, that will be looking to measure the properties of exoplanets, and other ones that are just totally dedicated to actually discovering the exoplanets and measuring a wide range of their properties. So we're going to have so much data on exoplanets, things worth thinking about. Is there any way we could exploit this large amount of data to find dark matter? Another benefit is we have very large statistics for exoplanets. So estimates are that there's something like billions of exoplanets in our galaxy. That's a lot if you have billion. Of course, you won't actually find all of these exoplanets in the immediate future. So to date, we have something like 5,000 confirmed exoplanets, which is a lot. 5,000 is a lot, but even just a tiny fraction of these billions of exoplanets would give us enormous statistical power to say whether or not dark matter is present in them. Another reason why they're good is they're fairly cold. So we have good signal over background. They're fairly large, at least compared to the tiny neutron star. They're roughly planetary size, so that's fairly detectable. And they also allow us to go to very low dark matter masses because some of them can be still fairly dense, big and dense. So we think of things like Jupiter or like super Jupiters, they're very dense and they can capture very light dark matter. So the type of candidates we want to actually use is not all of them. So when you think of an exoplanet, you might be thinking about Earth, but not just Earth somewhere else. And that actually is not the best one to use for exoplanet search. If you're Earth-sized, you may as well just use literally Earth most of the time. And we already have that data. We want to find something else. So Earths and super Earths, they're not ideal. They're small and they don't give us really any benefit. They're small compared to other types. They're not usually that much more dense. We don't get so much out of it. Instead, an ideal type of exoplanet are things called Jupiters and super Jupiters, which are just like Jupiter in our own solar system or a bit bigger. So these go up to roughly 13 Jupiter masses, and they're generally about the size of Jupiter. Another class we want to use are brown dwarfs. Now, brown dwarfs aren't really actually exoplanets. It depends how you actually classify all of this. There's kind of a blurry line as to what counts as a planet, what counts as some not quite star. But if you haven't heard of a brown dwarf before, it's pretty much just like what lurks between being a planet and a star. So we have no nuclear fusion, but they're burning deuterium. But these can be extremely dense. So their size can be, if they're old, roughly the size of Jupiter, but you can go up to say 75 times the mass of Jupiter, which means they have a lot of mass packed into the same area, which makes them very dense and very efficient at capturing dark matter particles. The other type that we really want to use is something called rogue planets or free floating planets. So these are planets that are cold, all alone, and just damned to wander through space, very, very cold. So these don't have a host star. They're not orbiting around another star. And these are great because then we don't have to worry about the host star heating up the planet too much. And particularly if we want to look very far into the center of our galaxy. And if we want to actually see one of these exoplanets, we don't want to have the problem we're looking so far away that we can't actually distinguish the difference between the host star and the exoplanet that's going around it. So even if you're on a very wide orbit, if you put this object very far away, you're just going to have no chance of being outshined. You'll just be outshined by the host star. So if we're looking very far into the center of the galaxy, we're only going to want free-floating planets, not bound planets, or brown dwarfs. So brown dwarfs often are just hanging out by themselves. In the local position, though, it will be okay if they're in an orbit, but they usually need just a sufficiently wide orbit that we can distinguish them from their host star and not get heated up by too much by their host star. We don't want an extra background. So one of, I think, my favorite benefits about using exoplanets that you can't get with most other objects is they actually give you potentially a probe of our dark matter profile. So the distribution of dark matter in our galaxy is really not known. So just to highlight this before I show you how the exoplanet data might look, this is just a sketch of a few different dark matter density profiles that come from simulations. So again, we don't really know all the details of what dark matter is up to, but depending on what you're doing in your simulation, you get a few different results for the shape. So on the x-axis here, this is distance to the center of the galaxy. So we're sitting roughly about 8 kiloparsec here. So to the left is going into the galaxy. And as you move inside, most of the time, what we expect really is there should be more dark matter there. So the y-axis is the dark matter density. So again, move into the center, we see more and more dark matter is sitting there. So because exoplanets are sufficiently big, the really cool thing is, so this is just mock data, we don't have the data yet. In principle, what should happen if dark matter is heated by exoplanets is they should actually trace this galactic dark matter density. And if this happens, this would actually give us a probe, not just from these simulations of how dark matter is distributed. And maybe we can learn about the exact details of how that looks. So the black dots here are just mock data, assuming one of these dark matter density profiles, just in a mock situation. And the magenta triangles at the bottom are the same exoplanets, but assuming no dark matter annihilation. So you see really the two different hypotheses give you very different answers. If dark matter is heating exoplanets, we expect this sharp uptick, increasing temperature as we move towards the center of the galaxy. If this isn't happening, we should pretty much just see a straight line. There shouldn't really be much correlation at all with the galactic position and the temperatures of the planets. This blue line here is what we estimate the sensitivity of JWST would be to this scenario. So we think at a rough estimate from this paper at least, you should be able to detect anything roughly above this line. Under the line, we wouldn't detect. So we should have some hope at actually detecting the slope of the dark matter density in our galaxy. So what data do we have? We have some data, but we have very little. So we haven't actually got the temperature of the right type of exoplanets just yet. Hopefully this is going to change very soon. JWST is actively measuring the temperature of many exoplanets. And these two I mentioned earlier, Robin and Rubin, might also be able to do this. But the limitations overall with this search are really just having enough acceptable candidates. So if you find ones that are all just way too young and way too hot, that's not going to work. We need to find enough kind of older, cooler ones where we can actually detect this dark matter heating. And then we need to understand a lot of the systematics a lot better, which is part of what we're looking at in some follow-up work. But there are many benefits, as I already outlined to you, including this density profile. In terms of the sensitivity to dark matter interactions, it can be pretty good. At least it's in the parameter space that hasn't been probed by anything else just yet. Again, y-axis is dark matter interaction size with scattering of protons, x-axis dark matter mass. So these shaded regions are just other existing experiments, including the deep underground experiments. And you see actually this little bit of the Earth peeking in here. So that's the Earth heating bound, but you notice how much better these other objects can do in terms of their reach. So this is excluded by the Earth. We can go much further down in the interaction size using something like Jupiter's or brown dwarfs. And this solid line of a dashed line is just depending on our assumption of how much dark matter is actually captured. So we kind of think if all dark matter is captured, you get the solid line. If there's some subfraction captured, you go about that far. We call it max because we think realistically that's the maximum you're going to be able to do given the telescope sensitivity. But it seems like there should be a new parameter space that we can probe. So what actions do we need for successful discovery or exclusion of dark matter? So a bunch of these things I told you are really just projections or thinking forward about how we could do it, but we don't robustly know yet if dark matter is there looking like this, heating up these stars and planets. So for neutron stars, really what we want to do is find a candidate sufficiently close by and old enough. There's hope, but might not happen. We also need enough observing time. If we do find one of these, we have to convince people to go actually look at them and look at the neutron stars long enough to say with some significance what its temperature actually is. For white dwarfs, we need to understand these astrophysical uncertainties and clusters in terms of is there actually dark matter in these clusters or not? And then also just more candidates in different locations. For exoplanets, we really want a large statistical sample. Your first hesitation might be like, how could you ever trust what's coming out of some heat increase in an exoplanet? Really, the key thing that we need here is just lots of data. Statistically, if you really get, tens of thousands of exoplanets and they're all hotter than what you would expect, you might say something's going on, particularly if it's correlated with this, uptick, which we wouldn't expect otherwise just from backgrounds. We also want to do some detailed studies of atmospheric effects, including dark matter, which we're discussing at the moment with some exoplanet experts, including Bruce McIntosh, who was at SLAC and Stanford as well. But there's lots still to be done. So just to give you a quick example of something we're thinking about now is we actually tried to answer the question better of how well you could extract the dark matter density profile, assuming you do get sufficiently good data from these telescopes. So the question would be, how many exoplanets do you actually need to say something statistically significant? And what level of precision do you need for all the parameters that you measure? So for example, the size, the temperature, and the masses. So I showed you before, here are some example profiles. You want to figure out what the right profile is for dark matter in our galaxy. And usually it's parameterized by something like this. So the dark matter density is a function of radius, so just the position in the galaxy. You have really usually like roughly 2 free parameters. So one is like the squishiness of the profile. So you could just take one of these shapes and then just like squish it in. That's really loosely talking about something called the scale radius, for those of you who have heard about before. The other one is like pointiness or cuspiness. And this is encapsulated by this like gamma parameter here. So for example, if you, this is something called an NFW, so Navarro-Frank-White profile. If you take this but increase the gamma, this is gamma 1, set gamma 1.5, you get something that looks kind of more peaked. So we want to try and extract these parameters. And we actually did a simulation with some mock data to see how well could we, if we had a certain number of exoplanets with a certain level of precision on our measurements, make some statement. And it turns out you could maybe do this with 10 exoplanets if you got lucky with the right exoplanets. So we did a bunch of simulations over and over again. I think realistically, we're probably looking at more like 100. But what this sort of grid is showing you on, it's a set for different amounts of exoplanets. So the top line is 10, next line is 100, and then 1,000. And each of the axes labels are squishiness on the x-axis and pointiness on the y-axis. And yellow is good, dark is bad. So if something looks more yellow, if those are the true parameters of the dark matter density distribution, we should be able to recover it fairly well. So if it turns out that the dark matter is more kind of flat, so these lower gammas correspond to something that's more what we call chord, not very like pointy, we wouldn't be able to use this search. So the general conclusion is probably works. We have to get enough data, but we'll only probably have information if the dark matter density profile is sufficiently cuspy or pointy. All right. How much longer do I have? 5-7. Okay. I'm going to, in the interest of time, just pick some of the most interesting bits of what's remaining. So far I told you about these heating searches. There's another type of search you can do. So one is you can use neutrinos. So if dark matter annihilates, it can produce neutrinos, which are very, very weakly interacting, just standard model particles. And neutrinos are so weakly interacting that actually, if you annihilate to them, they can just leave. So they can just get out and not be absorbed by the star or the planet. So if they just leak out, you won't get heating, but you can go looking for the neutrinos. So this is a signature that's been thought about before, and this is something we can detect with telescopes such as, for IceCube, Super K, a range of telescopes. Another thing is you can look for gamma rays. And the way you get gamma rays, this will depend on the dark matter sector that you have. But if you have dark matter particles that annihilate, and they annihilate with a lot of energy compared to the mediating particle. So usually we have a dark sector, dark matter particle, and then the standard model particles. And often in particle physics, we have to assume there's something we call a mediator that mediates the interactions between the visible sector and the dark sector. And if you have this annihilation that occurs with sufficiently large boost, or if this intermediate particle has a very long lifetime, it can actually just travel outside the object and then decay on the outside. So you have no heating, but gamma rays should be just showing up at the surface of stars and planets. And this has been done for a number of objects. I'm going to skip to my favorite one though, because I want to tell you about Jupiter. I found that a lot of fun. So the sun has been done. We thought about gamma rays from the sun before. Sun is great. We have lots of data. It's close by, so you get a lot of signatures. I'm just going to skip to the sort of sensitivity. So neutrinos has been done. Now here is the sun gamma ray limits, assuming dark matter annihilates with some long-lived particle making gamma rays. Very impressive sensitivity. We go many orders of magnitude below direct detection, assuming this is spin-dependent interactions. And this is limits we set already back in 2017 using Fermi data, which is just a gamma ray telescope. We pointed out that there was some sensitivity with, at the time, upcoming telescopes, so the Hawke Observatory and LASO, but they since started taking data. And we teamed up with the Hawke collaboration and then went looking and found nothing. So we already set very strong constraints using the gamma rays under this assumption that this is something dark matter actually does. But now, kind of interesting question is, what about something like Jupiter? So why would you ever want to use Jupiter when you have the sun, which is fairly close by and big? So very simply, why Jupiter? The sun is big, but it's hot. Jupiter is also big, a bit smaller, but its core is very cold. And what this means is that you have better sensitivity to very light dark matter because Jupiter is not so easily just giving these thermal kicks to light dark matter particles and make them leave. So compared to the sun, even though you have fairly strong sensitivity down on the interaction rates, you should be able to go to the left of these plots and probe even lighter dark matter masses using Jupiter. So this seemed like, in principle, it should have been a very trivial task. Probably, at some point, we already looked at Jupiter and gamma rays. We already had this set up for the sun. Probably, we can already just have a look if there's something there, set some constraint or point something out. But then it turned out, started looking through the literature, nobody ever looked at Jupiter and gamma rays, like ever. There was no paper existing looking at Jupiter and gamma rays. And this is why this was fun for me, because actually a big part of my research program that I'm not talking about today is doing gamma ray data analysis and thinking about new ways we can use gamma rays to try and find dark matter. So we already actually could use the Fermi gamma ray data, which is publicly available. Anyone can download it, analyze it, and have a look what's there. And we thought we would just go looking in the data and see if we can find dark matter there. And there were many benefits from this. So even if we don't find dark matter, we would have the first measurement of Jupiter and gamma rays. So that's just interesting to see what does Jupiter look like in gamma rays by itself. But also we could learn about astrophysics. So we could learn about how we might have acceleration of cosmic rays and Jovian magnetic fields. So it could tell us something about the magnetic fields, but also the interaction of cosmic rays with Jupiter's atmosphere. How does it look? How does it change things? Maybe dark matter is the fun part. So we went into the data, we downloaded it, we did the analysis. We took 12 years of Fermi data, which funnily enough, actually at the time was how long the Fermi Space Telescope had been running, but it's also actually exactly one orbit of Jupiter around the sun. So the way that we did this is we did it in a totally data-driven way, which is that we just kind of mapped out 45 degrees around Jupiter's orbit. So it's going around the sun. Fermi can see most of the sky at any time. Not all of the sky, but it sees a lot of it. So whenever Fermi could see Jupiter's orbit, it keeps we select that data. And anytime then when Jupiter moved into this 45-degree window, we called that the on region. It moves out, we keep taking the data, we call it the off region. And we want to take the difference of the on and the off region to see, well, when Jupiter moved into view, did we start picking up more gamma rays in its position than we would have otherwise? So we just want to look at the difference of when Jupiter's there and it's not there, does anything change? So here for the first time is what Jupiter looks like in gamma rays. The left-hand side is the counts. So this is like our on region. So for clarity, we choose a very large window of this 45 degrees. Jupiter is like 1 degree at this energy in the center. So it's like, it'd be like a dot in the middle is what you're looking for. And here's the background. This is when Jupiter's not in its region, but just looking at its orbit. How many gamma rays do we get? So here's the residual map, which is the difference of on and off. If Jupiter was emitting gamma rays, you should see something here. Nothing there. So Jupiter doesn't seem to be emitting in gamma rays, at least not within the sensitivity of the Fermi Space Telescope. Maybe it does, but it has to be below what Fermi would have seen. So, I mean, that's a bit disappointing, but we set the first upper limits on the flux from Jupiter. Nothing seems to be there. But if nothing's there, that also means we can set some constraint on dark matter's properties, because dark matter, if it annihilates to some long-lived particles, should have been making gamma rays on the outside, and we didn't see them. So that meant we actually could go much lighter dark matter masses. So see for the sun, the search I told you about before, that cuts off because the particles just get kicked out. And Jupiter instead will just continue. So we get excellent sensitivity compared to direct detection, these Earth-based experiments. So we have new constraints there. I'm going to skip over this last one. And before I wrap up, I told you only about a few types of signatures today. But in case you're interested in this topic, I just want to mention very quickly the range of things people actually do with stars and planets. I wish I could tell you about all of them, but it would take a very long time. So one thing people think about are like equation of state effects for neutron stars. And so if you have just really a lot of dark matter building up in these neutron stars, you can change, maybe you build up dark matter atmospheres, you can change the mass radius relation for neutron stars. And you can look at the in-spiral actually of neutron stars, and dark matter could change this. And this is a whole field of research, which is really exciting. You can think about dark matter in population 3 stars. So this is stuff that very early stars can change those. You can think about how dark matter actually changes how stars evolve. So if you have lots of dark matter, particularly very dark matter dense environments, it actually takes a different path on the HR diagram if there's lots of dark matter there. You can also actually create black holes from dark matter being in a star or a planet. If you make too much of it and the dark matter doesn't annihilate, it can make so much that it collapses into a black hole and then destroys a star or a planet. But then you could say, okay, we have stars and planets, so clearly this is not happening. So you could use this to set a constraint, and that dark matter cannot actually do this or have these type of interactions. Lots of different things. I also just wanted to mention something else you can do is think about exotic stars, maybe not regular stars or planets. And that's something that actually David Curtin and his collaborators have been thinking about here at Toronto. So this is a group of people all at Toronto thinking about mirror stars. So you should definitely chat to them if you're interested in thinking about exotic types of stars and what we could do there. All right, so to summarize, celestial bodies are really playgrounds for discovering dark matter. There's so many types of signatures you can look for, and there's so much fun you can have trying to find the right objects and putting it in the right place, and then thinking about what data we do or don't have to fill the gaps of where dark matter might or might not be. Today I discussed heating and very quickly neutrino products as well as gamma ray detection, which are possible. We already have strong constraints using the Earth, using the sun, and using Jupiter. In terms of our future sensitivity, we might want to use exoplanets, other planets, white dwarfs, and neutron stars. Maybe we'll learn what dark matter is or isn't using these systems. And overall, the reason why I'm excited about this field of research is just that we have so much data coming soon, and it's really worth thinking about how do we maximize our discovery for dark matter. Remember at the start of the talk, I told you we have almost no idea about what dark matter is. And really we want to throw everything we can at this problem. And there is so many of these objects actually will give us unprecedented insights to what dark matter is or isn't. So it's a great time to be thinking about how to use all this data across all these wavelengths across all of these objects. So a lot of these will come online soon. Lots of searches are coming soon, and hopefully also we discover dark matter. So that's all I wanted to say. Thanks a lot for your attention.